Okay, so today I'm going to talk about the other important topic which will continue, which is, of course, hydrogen bonding. So now I'm going to talk about the same intermolecular force, intermolecular hydrogen bonding. In hydrogen bonding, I would like to talk about H3BO3. So let's talk about H3BO3. So now I'm going to talk about this is known as boric acid. Now, what's the structure of this boric acid? Actually, this uh, boric acid, which is this boric acid. I'm going to take the marker. Mm, yeah, it's fine. Okay, let's take the boric acid. So this, let me talk about this boric acid. So this is also known as dimerization, right? Known as dimerization. What's the problem? Dimerization means something which is double in form, right? Dimerization. The H3BO3 does not found like this, it just found like this. First of all is dimerization, right? So this is the H3BO3 found something like this. H3BO3 whole twice. So H3BO3 found something like this, right? It does not found in a single form bi. And it is chelation, which is also a chelation. What we mean by chelation, we'll be each and everything in detail while we will make the structure. Chelation means something where we can encounter a ring. So in the structure of H3BO3, which is boric acid, we can encounter a ring. So it's called a chelation. So let's deal with it. Let's erase it. So remember this word, the dimerization found in HBO3 and also the chelation. So let's erase it and let's make a structure here. Okay, let me erase it. Okay, let's erase it. This one as well. Okay, so yeah. Let's take an example of, let's take this marker. So how we can make the structure of HBO3. This is B and then OH. O. Whether you can write together OH or just making this covalent bond or OH. Then OH. Then here as well O and then H. Okay, so now one more B O H. Okay, then again O H. Okay, so again here O H. So as you can see, this is A. We know the prototype that we created. In order to explain it, this is A H. So we will link the molecule or these atoms to this AHB. Okay. So this is A, this is H, and this will be the hydrogen bonding B. This is A, this is H, and this is B. As you can see, maybe it's not perfectly ring structure, but here you can see that we can encounter a ring-like structure, something like this. So this is known as chelation. We can find the chelation in this H3BO3, and why it's found in dimerization form, just because due to hydrogen bonding between two H3BO3 and H3BO3. So this is a basic reason why we can encounter the chelation with a ring in it and why it's found in a dimerization form. And one more example of dimerization is carboxylic acid. The formula of carboxylic acid is same. Same, we will create a structure and same reason is behind it. The why found in it also has chelation, its main ring, and we found in dimerization form. Right. So formula is R, which will kind group, COOH, and then whole twice. This is carboxylic acid. Right. So the same reason is behind H3BO3 as well. So this is basically carboxylic acid, which found in something like this. So it's what's written here is not for multiple series around the term mild antiseptic, antifungal, and antiviral properties. So we use for the different purpose. So we are done with it. Okay, let's erase it and let's deal with other. Okay, let me just move that side again so we can erase it. Let's erase it. Now I'm going to talk about the next, which is a special case where hydrogen bonding is found to be because of carbon. Hydrogen bonding is just found because of carbon. So let's take an example. Chloroform here, structure of chloroform. Let's take an structure of chloroform. Chloroform. Maybe my Wi-Fi is not working properly. So we can take the example. Okay, picture is taking a bit too long to get load. So let's deal with it without having that picture. Picture is not needed, so I can explain without this one. So for example, this is the formula of chloroform. Now we have to tell, the question is here that this is a special case. Remember, this is the special case, where hydrogen bonding where hydrogen bonding is formed due to not it's governance formed due to carbon. Hydrogen bonding is formed due to carbon. So let's see with it. Let's erase it on our new marker for the picture. Okay, so now we are aware of the formula of chloroform, which is CHCl3. CHCl3 chloroform. CHCl and the other propanol is CH3COCH3. This is the formula of propanol. CH3CO CH3, again CH3, CH3, CH, though I'm writing the name here as well. So let's take this color. You can appreciate chloroform, and CH. This is propanol. So I'm writing a short form here, propanol, that you can know this for the name propanol. So how it creates a structure? We create a structure something like this, which is, this is basically carbon, one chlorine, other chlorine, and one more chlorine. Then here hydrogen. And what's the structure of this? C double bond O with a lone pair, and CH3, CH3. So what happens? That we know that chlorine is electronegative in nature after fluorine, right? So this chlorine attracts the electron from carbon atom, get a partial negative and negative charges, due to which carbon becomes electropositive, gets a partial positive charge, right? And what happens? This carbon becomes electronegative and attracts a hydrogen electron toward itself, due to which the hydrogen gains the partial positive charge. And when hydrogen gains this charge, the hydrogen wants electron, and this oxygen shares give its lone pair to this hydrogen, due to which they create a hydrogen bond in between them. So here the hydrogen bond is formed just because of this carbon, which become electronegative when the chlorine, yes, where the chlorine attracts the shear pair of electron toward itself, it is high electronegativity, right? So this is a reason, or this is a special case where carbon act as a reason behind the hydrogen bonding. So yeah, this is the reason behind hydrogen bonding. Now let's deal with the other question. So let me just erase it. We are one by one dealing each and every question with the answers as well. So what's the exact reason behind it? If it's happening with why? What's the reason? Right? So we are dealing with each and everything with concept. Okay, let's deal with other. Okay, so let's see with other. I think its picture is not needed. Now let's read it. So the other question arises that which has more solubility. The next question is that. Okay, so let's erase it. Delete. The next question is that. But let me just erase the complete board. Okay, so the next question arises that which has more solubility in water. Solubility in water. And we have two options that we have gotten. One is NH4 positive, NH4 positive, and the next one that we have is that we have Na positive. So let's create a structure here so that we can have an idea which one is right and which one is wrong. So first I'm going to make the structure of Na. We know that the Na is a sodium ion. This is cation, sodium. We know the water molecule is surrounded by this cation, something like this. Let's see. 1, 2, 3. This is only an example, right? So here we have oxygen and then we have hydrogen. I'm not making hydrogen here. Oxygen and oxygen. So as you can see there, this is a bond between oxygen and sodium. Oxygen and sodium. So which bond is this? This is ion. This is dipole molecule. This is ion dipole interaction. This is ion dipole interaction. This is hydrogen. Going something like this. Hydrogen, hydrogen. This is ion dipole interaction. On the other hand, we have other example as well. So let's deal with an example as well. For example, we have a molecule. We have NH4. So NH4 is structuring something like this. H, H, and H positive. H positive. This is water, which is OH, and one more H is here, something like up. So this hydrogen makes the bond with the lone pair of electrons. So this hydrogen makes the bond with this hydrogen, due to which it has hydrogen bonding. As you can see there, A, which is A, H, B, hydrogen and oxygen. F, this is the bond between hydrogen and oxygen. This is the bond between, this is ion dipole interaction. This is hydrogen bonding. So it has more hydrogen bonding, right? This is more soluble in water. Whenever it forms strong hydrogen bond with water, then we can encounter the hydrogen bonding. So next, let's move toward the next question here. So let's erase it. Let's move toward the next question. Okay, I'm writing the question here, which is more soluble in water? Which is more soluble in water? So then we have, for example, two examples. First is ROH, which is alcohol, and the other one is RNH. RNH. I don't know how to make the complete structure that they're making here, but I'm only writing here. One is alcohol, but the other one is we have an amine. Alcohol and amine. So RNH is amine and ROH is alcohol. So let's make a structure here. First of all, ROH. Journal structure. RO, this is alcohol. Let's begin again. R R O, this is O, then H, then again R, then again R, N, H, this is H, consider this H is H, and here H. So this is amine, this is what alcohol. So which one is more soluble in water? Right? Let's see. For example, the first bond of ROH with water. Let's see how it does look like. R, this is a bond. I have forgotten the name. R O H O H H. So this is hydrogen, this is oxygen. It has one nucleus. So it can make a bond with this oxygen. So as you can see, this is A, this is H, this is B. What criteria we have to follow for counter which one is stronger is that A should be high electronegative, H should be hydrogen, and B should be electronegative but less than this. Okay, so it should be electronegative in nature. So let's see with the other one, but less than this. Right. So let's see it be with this phenomena, which is N. There is something like this. RNH3 R. So let's erase it for making it properly. So let's go. This is RNH R N N R N H and again H, and this is H O H H O H H. So this is a bond between oxygen and hydrogen and oxygen. So it is also forming AHO. Since this nitrogen is less electronegative, but this oxygen is more electronegative, so this is more soluble in water. Right, so this alcohol is more soluble in water, but this is less soluble in water. So let's see with the other questions as well. So that will be the last questions. Okay, let's do that as well. Okay, so I'm just generally writing here. There is no need to write it. So they are asking tell me which has a high boiling point, which is high boiling point, which has high boiling point. First we have HF, halides of HF, then HCl, then HBr, then HI, hydrogen iodide, HI. So most of us, what we have studied, van der Waals is dependent upon the van der Waals molecular weight. So it has high molecular weight due to which it has high boiling point, but no, this is the wrong. It has one exception, that this hydrogen bonding is a strong bonding among all the van der Waals forces. The first is hydrogen bond HF, then rest of the order is just same. So first we have to take the hydrogen fluoride because it is the highest bonding point. Highest. It is the highest among all these given options. So this is highest, right? So this is some of the concept.